happening. I think your question is, will it always be partial fractions? It's not. Understand? I want you to do those for homework, though. I don't want to work through that one. All right. We're going to move on. 8.3. 8.3, here's what we're going to cover in 8.3. We're going to do what's called the integral test. We're going to talk about what are called p-series. And we're going to do what's called the comparison test. Oh, no, your test stopped at the end of last class. What's on your test, your take-home test? That's material that ended last class, all right? So this stuff will be on the final. The final is going to be pretty intense, I guess. The final is going to be mostly just chapter 8. Yeah, there's no way I could make a final that could cover everything in a reasonable amount of time. Unless y'all want to do a 12-hour final. No, not interested. We can have like a pizza break in between, 6 hours in. No? Take a nap, that's fine. All right, let's do integral test. All right? Now look on your sheet and look up the integral test, and let's just take a look at what it says, because it's important that you can read this. The integral test says that you can be working on, again, any series. And then below it they have this weird thing, a sub n equals f of n. What this is telling you is that you're going to take the formula for the sequence and you're going to convert it to a function. Now we did this when we were trying to use L'Hopital's rule. Remember how we said we had to switch over from a function that's defined only on the natural numbers over to a function of x so we could do L'Hopital? Same sort of thing here. With integrals, right? We need nice functions. We can't do integrals of sequences. So that's why it has that. And then what's the conclusion here? What does it say? It says if the integral from 1 to infinity of the function f of x dx converges, they put converges in front. I'm just going to put then so does that. And then if this integral diverges, then so does the series. I'm going to draw you a picture in a minute. But there's something else on the side that is kind of just subtly sitting there. And you may think it's not important, but this is absolutely critical, this last little column over here. What does it say about that function f? It has to be continuous. What does that mean? Yeah, you basically don't have any jumps, like breaks in the graph. It's okay to have points, okay? But you just can't have like a jump or a hole. All right, so it's got to be a continuous function. What else does it have to? Has to be positive. What does that mean? Above the x-axis. Your function must always be above the x-axis. And then it has to be decreasing. What does that mean? Negative slope. So that means if you were to draw it, it's coming down, right? It's coming down. Now, that formula sheet is a little bit weak when it comes to this particular thing. I want you to put next to this, somewhere on there, I know it's hard to squeeze it in there, eventually. You do not need that the function is always decreasing. You just need it to eventually be decreasing and stay decreasing. So in other words, your function might go up, but eventually it comes down, and it always goes down. And then what's the last thing? It has to be integrable. That's a weird word. Integrable. And that just means you need to be able to integrate it, because guess what? We're going to do an integral, right? So you better be able to integrate it. All right, now let me try and draw a picture and try and convince you of why this test works. I want to take a very simple series to start here. Let's go with 1 over n squared. Okay, 1 over n squared. Remember, this means, and let's start n equals 1 to infinity. This means 1 plus a fourth plus a ninth, right, plus a 16th plus dot, dot, dot. Yeah? Now, I'm going to do this with a picture. If I plug in 1, when I plug in 1 into this sequence, I got 1, right? So at 1, I got 1. I'll put that right here. And if I measure it like this, if I get my ruler out, sorry, my thing keeps on going. Okay. I hate to do this. I'm gonna have to stop this real quick. Okay, so now when we plug in 1, right, we get this. So imagine it's like a length that we could sit here and measure, right? That's 1 unit long. And then we plug in 2, we get a fourth, which would be about here. And we measure the length of that, that's 1/4. We add the two together, right? 1 plus a fourth, that's the first two. So it's almost like you're taking this one, stacking it on top of that one to get the first two, right? Then you go to the next one, 1/9, and you keep doing this, right? So it's, imagine taking all of these and just trying to stack them on top of each other. Does that make sense? That's what this sum is? Mm-hmm. So how in the world does the integral come into this? Well, think about the integral. If I switch this over to the function f of x is 1 over x squared, then all those dots are going to lie on this function, aren't they? So imagine connecting these dots with the curve like this, right? And now I'm going to come in here with a separate little image here, a little geometric shape for you. What if I draw a rectangle like this? Tell me about the area of that rectangle. What's the area of that rectangle right there? No, the green one. Isn't it? How wide is it? 1. How tall is it? The blue length, right? So isn't the area of that 1? Okay, what if I extend this rectangle right here? What's the area of that? 1/4? And what's the area of the next one? 1/9, right? Wait a minute, hold on, 1/4. Yeah, 1/9. Do y'all understand what I'm doing here? Those rectangles, if I add those rectangles up, the areas of those rectangles, I would be adding 1 plus a fourth plus a ninth, which is pretty much the same as this, isn't it? But those rectangles, the area of those rectangles, right, are going to be following the integral area. Now, they're not exactly the same. Okay, so look, the area of the red, that's what we would get from the integral, right? Mm-hmm. But the greens are going to stay within a finite number, right? Like if this is a finite number, this is going to be finite. If this is finite, that's finite. If this is finite, that's finite, right? So if the red one if the red area converges, the green area converges, which means that this sum converges. On the other hand, if the red area is divergent, and the green areas would be more than that, wouldn't they? Then this should diverge. And that's what that, if you read off that table again, it says, if the integral converges, the series converges. If the integral diverges, the series diverges. So whatever the integral does, the series does. Understand? It's a nice test. Now, I don't like using it that often, but it's good to have. So let's actually do this problem with the integral test. Okay? Here we go. So I look at it. I run the nth term. Nth term fails, right? Nth term fails because the limit of that goes to 0. So that fails. I look at it. It's not geometric because the n is not in the exponent, right? Now, I understand it is a p-series, but we haven't talked about p-series. So it's not harmonic, right? It's not a constant over a linear. How about telescopic? You wouldn't be able to split that up using partial fractions. Because if you try using partial fractions on this, you're actually going to get right back to this. Like it's going to be the same expression. So you can't do any telescopic on it. So then I say, well, maybe it's integral test. And the first thing that I like to think about when I think integral test is if I convert that to a function of x, do I even want to try and integrate that? Like, yeah, I'm not intimidated by that, right? That's an integral that I'm willing to do. So now I need to go through and check to make sure it meets all the conditions. First, is f continuous? And you must show this. Look, if you're going to use the integral test on an exam, you must run through all these things. If you don't, you're going to lose 40% of the credit. Because you can't just arbitrarily throw an integral test without checking that it satisfies the criteria. So is f continuous? Is this a continuous function? Not always. On 1 to infinity, yes, right? It's discontinuous at 0. But we're only looking from 1 to infinity. Why? Because our sum goes from 1 to infinity, so our integral is going to go from 1 to infinity. So we're good there. What's the next thing? Is f positive? Well, this is easy. 1 over x squared. Is that question mark greater than 0? I hope you agree. Positive number on top. Anything squared is positive. So the ratio of two positive numbers is positive. So this is positive, with the exception that x is 0, but we've already eliminated that as a possibility. So yes, it is positive. What's next? Is f decreasing? Now there are several ways to show that a function decreases. You could start plugging numbers in and just show, we showed earlier it was 1, then 1/4, then 1/9, right? It's getting smaller. That's obvious. But what's the actual, true procedural way to show that a function decreases? The derivative, right? You run a check on the derivative. If the derivative of a function is negative, it's decreasing. If the derivative function is positive, it's increasing, right? And if it's 0, then it's flat. So all I'm going to do for this is run a quick check on the derivative. What is the derivative of this function? Negative 2 over x cubed. Now, what you have to keep in mind here is that the original function is x to the negative 2, right? So we're doing the derivative, not antiderivative. Negative 2 comes out, subtract 1, we get this, right? Drop that x to negative 3 down. My question is this less than 0? Is that a negative number? Well, the numerator is always negative, right? The denominator would then need to be positive, right, for this to be negative? Is x cubed always positive? Yes. Yes and no, right? Yes on 1 infinity, no in general, right? So this is true, yes, on 1 infinity.